Today's video will take you inside the most stubborn mistake people make about electricity, and I'm going to dismantle it the way Richard Feynman would in a lecture, with the parts that feel wrong at first and then suddenly become unavoidable. This is a presentation in a voice and style inspired by Richard Feynman, and the notable thing here is simple. The picture almost everyone carries around in their head is comforting, intuitive, and fundamentally misleading. They imagine electrons hauling energy through copper like freight. Meanwhile, the real action is happening in the space you ignore. We'll look at the instant light bulb problem that embarrasses the water pipe story, then follow what actually moves fast when you close a switch. We'll take a few sharp turns. Energy flowing where you cannot see it. The strange role of surface charges that quietly arrange the whole circuit. Why coax cables and transformers expose the truth, and why people keep mixing up drift speed, signal speed, and power flow. If you get this wrong, you can still do homework. If you get it right, you start thinking like physics. Now let me put you at the switch. The first time I realized how badly we lie to ourselves about electricity, it wasn't in a textbook. It was in that awkward little gap between what my hands could do and what my brain thought it understood. You flip a switch, and the room obeys. The lamp jumps to attention like it's been waiting. That instant obedience seduces people into the laziest story imaginable. Electrons must be racing through the wire like water in a pipe, hauling energy from the source to the bulb. A nice, comforting picture. You can point to the copper and say, that's where the action is. But then you do one sober calculation, and the whole thing falls apart. Inside a metal wire, the electrons drift. Drift. Not sprint. Not even jog. They shuffle along at a speed that, in many ordinary circuits, is closer to the pace of a crawling bug than anything heroic. Yet the lamp doesn't wait for a single electron to travel from the switch to the filament. It lights up essentially as soon as the circuit is completed. So either the lamp is cheating, or our story is trash. Here's the question I want you to sit with, because it's the kind of question that separates people who memorize from people who understand. If the electrons are moving slowly, what moves fast? Now, I can imagine two kinds of worlds. In the first world, the water analogy wins completely. It becomes the official myth. Children are taught that current is like water, voltage is like pressure, and energy is carried by the moving stuff inside the wire. The analogy spreads because it's easy, and because it flatters our eyes. You can see pipes. You can see wires. In that world, the public is permanently confused. They argue about whether electricity moves faster than light, as if it's a race. They picture batteries as little tanks full of electron juice. They think power is something sloshing inside copper. And every time they run into a phenomenon that refuses to behave like plumbing, they patch the story with more metaphors until it becomes a swamp. In the second world, the story is told differently from the start. Not more complicated, just more honest. In that world, you don't begin with electrons as tiny marbles marching through metal. You begin with what actually pushes and pulls, the electric field. You treat the wire as a guide, not as a pipeline full of energy. You admit something that feels almost rude because it removes the wire from the starring role. The energy mostly travels in the space around the conductors, in the electromagnetic field, and the wire's job is to shape that field. That second world would feel like magic to the first one. People would say, how can energy travel through empty space? But the space isn't empty in the sense that matters. It's full of the field, and the field has energy and momentum as surely as a moving object does. The field isn't a metaphor. It's the thing. Now here's the best part. Once you accept that, the instant lamp stops being mysterious. The signal, the reconfiguration of the electromagnetic field, propagates quickly through the space around the circuit. That propagation is fast because it is tied to how electromagnetic influences spread, not to how fast individual charge carriers drift. The electrons respond locally. Every electron along the wire gets the message and begins to drift almost at once, like a long line of people in a crowded hallway who all start moving when the pressure changes. Nobody has to run from the back to the front to make the front move. The push is communicated. Let me push the what if one notch further, because it exposes how deep this goes. What if, from the earliest days of electrical engineering, the mental picture wasn't current or wire, but energy flow in a field? Imagine how many arguments would evaporate. The false debate about whether electricity is inside the wire would never happen. People would naturally ask better questions. How does the surrounding space store energy? How is energy guided? How do boundaries and geometry shape it? How does the field rearrange itself when you close a switch? And the practical consequences would be enormous. You'd stop treating circuits as abstract loops on paper and start seeing them as three-dimensional field problems, even when the field behavior can be simplified into circuit rules. You'd teach why transmission lines matter without treating them as some advanced, annoying exception. You make sense of why a coaxial cable carries energy in the dielectric between conductors rather than inside the metal. You'd understand why you can move energy from one coil to another without a direct wire connection. You'd also understand why a badly routed ground can ruin your measurement even if your schematic looks perfect, because the geometry changes the field, and the field is where the action lives. Now, I know the immediate objection. I can hear it like a heckler in the back row. If the energy is in the field, why do we need the circuit at all? Why can't the battery just send energy through space to the lamp without wires? Good. That's the right kind of annoyance. Hold on to it, because the wire is not irrelevant. The wire is a constraint, and constraints are powerful. The conductors force charges to arrange themselves on the surfaces in just such a way that the electric field lines thread the space, curve around bends, and establish the pattern that drives the current. Those surface charges are tiny, almost insultingly small, but their job is huge. They sculpt the internal field that makes charges drift, and they sculpt the external field that guides energy flow. In the world where we taught this early, people would stop thinking of a circuit as a loop of stuff and start thinking of it as a negotiated arrangement between charges, conductors, and the surrounding space. Close the switch, and the negotiation happens quickly. Charges redistribute. Fields rearrange. Energy begins to stream through space toward where it will be dissipated. So here's where I want to take you next. Not with slogans, but with a concrete picture you can almost draw on a chalkboard. A battery, two wires, a resistor, and the space around them treated as part of the apparatus, not as blank nothingness. If you follow that picture carefully, the old pipe story won't just feel wrong, it will feel impossible. If you follow that picture carefully, the old pipe story won't just feel wrong, it will feel impossible. And that's not a poetic complaint. It's a physical one. Picture the simplest honest circuit you can draw without lying. A battery, two wires, a resistor. Now stop thinking of the wire as a tube and start thinking of it as a boundary condition, a constraint in space. The moment you close the switch, charges on the surfaces of the conductors rearrange themselves. Not because they decide to, but because the laws force them to. Those tiny surface charges build an electric field inside the metal that points along the wire. That internal field is what makes the electrons drift. But the same arrangement also creates an electric field outside the wire, in the space around it. Meanwhile, the current creates a magnetic field curling around the conductor. Where those fields overlap, something precise happens. Energy flows. Not metaphorically, not as a story, but as a vector quantity in space. The direction is given by the cross product of the electric field and the magnetic field. One field points roughly along the circuit, the other wraps around it, and the resulting energy flow points mostly through the space alongside the wire toward the resistor, then into it. Into it. That is the detail that usually shocks people. The energy doesn't have to travel inside the copper to arrive. It arrives at the resistor from the surrounding field. Now I want you to imagine a best-case history where this becomes common sense early. The way the idea that air has pressure became common sense after people stopped treating nothing as literally nothing. In that world, the first time a student asks, "Why does the bulb light so fast?" the teacher doesn't hand them a plumbing analogy. The teacher says, "The electrons are slow, but the field rearranges quickly. The field carries the energy, and the wire guides the field." And then the student asks the second question, the better one. If the energy is outside the wire, where exactly does it go? This is where the story gets deliciously concrete. The energy streamlines bend and converge into the resistor. In a real resistor, the electric field exists inside the material and does work on charges. The charges collide with the lattice, transferring energy into heat. You can call it Joule heating if you want to sound official, but the point is simple. Energy that was in the field ends up as random motion of atoms. The resistor is an energy sink. The wire, ideally, is not. That sounds like a small correction, but in a classroom it's a revolution, because now you're teaching power as something that has a location in space. You're teaching that the space around the circuit matters. You're teaching that geometry is not decoration. Here's one alternate path that comes out of that immediately. What if electronics education had always treated a circuit diagram as a map, not the territory? In that world, the moment you draw two long wires separated by a gap, you'd ask, what does the field do across the gap? You'd see that even with a break, the field can still couple across space like capacitor. Tiny energy can transfer briefly. You can get a transient response, a little kick, because the changing field can do work even without a complete conductive path. But you don't get sustained power delivery because you don't get the steady cooperation of both fields. No continuous current means no sustained magnetic field pattern, and without that partnership, the energy flow structure doesn't hold. This single distinction, transient versus steady state, would have saved the world an ocean of pointless arguments. People wouldn't get hypnotized by one dramatic demonstration and then act surprised when an engineer says yes, but that's just the initial behavior. Both are real. They are different regimes. Nature does not care about our desire for one clean story. Now let's go even further into this best-case timeline. If you teach fields early, you also teach humility early, because the field picture makes you see how much is going on that you can't see. It makes you comfortable with the idea that the mathematics might be cleaner than your intuition. The pointing picture looks crazy at first because it tells you the energy can flow in directions that do not match the direction of the current. That's exactly why it's good. It forces you to stop trusting the wrong mental images. And once you're comfortable with that, something interesting happens to technological culture. In the plumbing world, people obsess over the speed of electrons. They talk about electricity traveling at near light speed and then get confused when someone points out drift velocities. They treat these as contradictions. In the field world, those aren't contradictions at all. Signal propagation speed is about how fast the field information travels through the electromagnetic environment, which depends on the medium and geometry. Drift velocity is about how fast charge carriers creep under the influence of the internal field. They are different questions, different answers. No drama required. In a best-case world, this changes how we design things. Grounding isn't superstition, it's field shaping. Shielding isn't magic foil, it's boundary control. Crosstalk isn't leakage, it's field coupling. Even the idea of a short becomes clearer. You're changing the field configuration, so energy prefers a different route. Now, let me offer you a second alternate history that I find even more entertaining. What if the public had been taught that energy flow can be drawn in space the way you draw streamlines in fluid flow? Imagine popular magazines in the middle of the 20th century printing diagrams of energy streaming from power plants along transmission lines, not as electrons racing inside metal, but as fields guided by conductors and dielectrics. Imagine children growing up knowing that a coaxial cable is like a corridor where the energy walks in the space between two conductors, not inside either one. That one visual would have made half the arguments on the planet evaporate. And then, if you're really bold, you start connecting it to the deeper unity of physics without getting lost in mysticism. You say, look, classical electromagnetism is already astonishing. It already tells you that the vacuum and materials can store energy in fields, that changes propagate, that energy and momentum can flow without a piece of matter carrying them like a suitcase. If later you want to talk about the quantum picture, fine, but you don't need it to understand why the lamp lights. The field picture is already enough to break the pipe illusion and replace it with something you can actually trust. So where does this leave us? It leaves us with a challenge that feels almost philosophical, but is really practical. We must stop explaining electricity in a way that's easy to say and hard to unlearn. If you care about understanding, you want explanations that are slightly harder at first and much easier forever after. And next, I want to show you the most unsettling version of the instant lamp idea, the one that makes people squirm, because it forces you to choose between the pretty pipe story and the field story. You can't keep both. Only one survives the geometry. You can't keep both. Only one survives the geometry. So let's do the cruelest experiment you can do to a bad intuition. Stretch it until it breaks. Imagine a battery and a lamp, perfectly ordinary, sitting on a table. Now imagine the connecting wires are not the little polite links you use in a classroom. Imagine they run away from the table, out the door, across the city, across the country, so long that light itself would take a noticeable time to go from one end to the other. Don't picture a long wire. Picture something absurdly long, because absurdity is where the truth stops hiding behind comfort. Now, if you're still married to the pipe story, you must say something ridiculous. You must say, the lamp will wait until the electrons have marched through those wires, delivering energy like couriers. That would mean you flip the switch and then you stand there in the dark, possibly for seconds, minutes, or longer, while electrons do a cross-country jog. But the lamp doesn't care about your marriage to that story. The laws don't care either. In the field picture, the moment you close the switch, the electromagnetic conditions at the battery terminals change, and that change propagates outward through space and along the conductors at a speed set by the electromagnetic environment. The lamp can begin responding as soon as the field change reaches it through the space and geometry that connect them. The charge carriers in the lamp don't need a fresh batch of electrons shipped in from the battery. They already have plenty of charges sitting right where they are. What changes is the field that tells them how to move. This is where people start to squirm, because they want one story that covers everything. They want to say either it lights instantly, or it must wait for a complete loop. Nature does both, depending on what you ask and how you ask it. If there's a gap, you can still get a tiny response because the system behaves like a capacitor for a moment. Energy can couple through the changing electric field across space, just as it does in any capacitive arrangement. You might even see a brief flash or a measurable voltage, depending on how sensitive your setup is. That initial response is real, and it is the kind of detail that lets sloppy explanations cause wars. But sustained power, the kind that makes a lamp glow steadily, needs the full arrangement to settle into a steady state. That means the field has to establish itself along the entire geometry. And in practice, that means the behavior is tied to transmission line physics. The signals and reflections and delays are not special effects. They are what you get when you stop lying and start treating the circuit as a physical object in space. Now, here's a best-case scenario that follows naturally. What if everyone learned early that circuits are not just loops, but electromagnetic structures with a time history? In that world, nobody would be shocked when an engineer says the first nanoseconds of a circuit's life can look different from the next millisecond. Nobody would talk as if DC means nothing is happening. They'd understand that steady state is the calm after a violent, fast-settling process. They'd also understand why certain classroom questions are traps. Not malicious traps, but traps for the wrong mental model. That world would produce a different kind of curiosity. People would start asking, where is the energy stored before it reaches the resistor? What is the battery actually doing in the first instant? How does the system decide what pattern of surface charges is needed so the internal field points around corners? And that's where the story becomes almost tactile. Think of the surface charges as tiny sculptors. When you close the switch, they rearrange along the conductors until the electric field inside the metal has the right direction and magnitude to drive the current that matches the circuit's constraints. At bends, at junctions, near resistors, the distribution adjusts because the field has to turn. This turning is not done by electrons politely taking a corner. The field is what turns, and the surface charge distribution is the mechanism that makes it turn. In the bad pipe story, corners are nothing. In the field story, corners are everything. A sharp bend changes capacitance. It changes inductance. It changes the way fields concentrate. It can radiate. It can reflect signals. The geometry writes the rules in the margin. Now let me give you another alternate history, because it illustrates the cultural cost of getting this wrong. What if, during the early explosion of radio and electrical power, educators had insisted on field literacy the way they insisted on literacy in reading? Not to turn everyone into a theorist, but to inoculate them against nonsense. In that world, the public would have understood why antennas work. They would have understood why you can transmit energy without wires at all. They would have understood that wireless is not the absence of physics. It's the direct use of fields in free space, with all the usual constraints. And in that world, the phrase "electricity is flowing through the air" would not sound like a mistake. It would sound like a crude but essentially correct observation. Energy can move through space via fields, and conductors are one way, not the only way, to guide that energy. The best-case version of that history would have a peculiar benefit. It would make people less gullible about science and more demanding about explanations. They would learn early that a model can be useful without being literal. The water analogy becomes a temporary crutch, not a lifelong belief. You use it to introduce the idea of continuity, of a conserved flow, and then you toss it away before it calcifies. Now, I can't resist one more what if, because it makes me smile. What if the dominant metaphor for electricity had been traffic of influence instead of flow of substance? In that world, we talk about the field as the message and the electrons as the crowd responding locally. We'd stop imagining energy as a thing inside the wire and start imagining it as a relationship distributed in space. People would stop asking, "How fast are the electrons going?" the way they ask, "How fast is the news traveling?" They are different speeds because they are different things. And that brings us to the edge of the conclusion, where the real punchline lives. The misconception persists because we trust our eyes too much. We see wires. We don't see fields. So we assign the job of energy transport to the visible object. But the universe isn't obligated to route power through whatever object happens to be easiest for a human to point at. The honest picture is stranger and better. The energy takes the path permitted by the electromagnetic fields, shaped by conductors, stored briefly in space, and delivered where it can do work. Once you see that, you start noticing it everywhere. In transformers, in transmission lines, in the way a circuit can behave like an antenna when you didn't intend it to, in the way a shield can make a problem disappear without touching the current at all. And next, I want to bring it home to the simplest human experience again. Flipping the switch, not as a magic trick, but as a fast, beautiful reorganization of the fields that fill the space you live in, whether you acknowledge them or not. The thing that still makes me laugh, even after you've stared at this long enough to lose the novelty, is how ordinary it feels once you finally stop lying about it. You flip a switch and a lamp turns on. The world doesn't wobble. Nobody applauds. Yet that tiny action reorganizes electromagnetic fields throughout a chunk of space around you at a speed that makes your everyday sense of cause and effect look slow and clumsy. If you want a best-case version of human understanding, it starts right there, taking the most familiar act in your house and refusing to accept the lazy story about it. Because the lazy story always sounds the same. It says energy is a substance and wires are pipes. It says electrons haul that substance from the battery to the bulb. It says the wire is where the power lives. It gives you something you can picture with your eyes, and it buys your agreement by being vivid, not by being true. What I've been trying to do is replace that with a picture that is less cozy and more accurate. The energy is in the field. The wire guides the field. The charges drift locally. And the whole system comes to life by setting up a pattern in space. Now, here's the final what if I can't resist, because it turns this from a neat correction into a real cultural test. What if we treated this misconception the way we treat bad medicine? Not as a harmless simplification, but as something that creates downstream damage. In that best-case world, we'd stop telling students the pipe story as if it were almost true. We'd say, it's a temporary analogy for a few minutes, and then we throw it away before it ruins your instincts. We'd put the field story in the center early, not with heavy equations and heroic symbols, but with simple truths. Fields can store energy. Fields can transport energy, and geometry matters. If that happened, the ripple effects would be everywhere. People would become harder to fool with technical-sounding nonsense. They'd ask questions like, where is the energy density highest? What boundaries guide it? What sets the timescale? What changes in transient behavior? What is the steady state? They'd start noticing that many mysteries in technology are not mystical at all. They are field problems pretending to be circuit problems. And they'd also get a more honest relationship with models. A good model isn't one that feels intuitive. A good model is one that keeps paying rent. The pipe story pays rent for about 1 week. Then it becomes debt. The field story feels a little weird at first, but it pays rent forever. It explains why a coaxial cable behaves like it does. It explains why a transformer can pass energy across a gap without any electrons jumping the gap. It explains why long wires and high frequencies force you to think about waves, reflections, and delays. It explains why shielding works by shaping boundaries. It explains why a circuit on a breadboard can act like an antenna and spray trouble into the room. Now, let me tie back to that moment from the beginning. The moment when your hands flip a switch and your brain tries to tell a story. In the pipe story, the switch lets electrons out, and they rush to do work. In the field story, the switch changes boundary conditions. That change propagates. Surface charges redistribute. The electric field inside conductors establishes the drift. The magnetic field wraps around that current. Together the fields define an energy flow in space. That flow converges into resistive elements where energy is transferred into heat and light. So when the lamp lights, it is not because a particular electron has traveled from the battery to the filament like a messenger carrying a glowing envelope. It is because the electromagnetic environment has been rearranged so that charges already near the filament begin doing organized work. That is a very different story, and it has an emotional consequence, whether people admit it or not. It teaches you to respect the unseen structure of the world. We tend to worship what we can see. The wires are visible, so we give them credit. The fields are invisible, so we treat them like optional poetry. But the invisible thing is the main event. Now I'll end where I began, with a choice between two worlds. In the first world, we keep teaching the easy lie. People keep thinking of energy as a substance flowing in copper. They get confused about speed. They get blindsided by transmission line effects. They argue about demonstrations as if one dramatic setup proves everything, and they carry around an intuition that fails them the moment they try to build or understand anything subtle. In the second world, we teach the harder truth early, in plain language, and we accept that reality doesn't owe us a picture that looks like plumbing. In that world, students grow up knowing that empty space is not empty of relevance, that fields can carry energy, that geometry writes physics, and that many of the most powerful ideas in science are the ones that feel slightly wrong at first. If you want a simple takeaway you can keep without turning it into another myth, it's this: the wire is the guide, not the cargo train. The energy mostly travels in the electromagnetic field around the conductors, and the charges in the metal are the local participants that make the field pattern possible. And if you really want to test whether you've absorbed it, don't repeat the words back to me. Do something more honest. The next time you see a circuit, imagine the space around it as part of the machine. Imagine the fields as real geometry. Ask yourself where the energy is, where it's going, and what shapes it. The moment you start asking those questions naturally, the old pipe story will feel like what it always was: a cute picture that couldn't survive contact with the actual world. I like endings that don't feel like the lights went off, but like somebody opened a window, because that's what this whole journey really is. It's not about wires. It's about the habit of mind that keeps us honest. The world is full of convenient stories that sound right because they're easy to picture. And the trouble with an easy picture is that it can get promoted from helpful to holy, and then it quietly blocks your ability to see what's actually happening. A switch clicks. A lamp answers. And for most people, that's the end of the thought. But if you let yourself sit with it, really sit with it, you start to feel the strangeness underneath the ordinary. The space around the circuit is not dead space. It's an active participant. The arrangement of conductors is not just a route. It's a set of constraints that shapes what the fields can do. The charges inside the metal are not heroic couriers carrying little packages of energy down a copper highway. They're local responders, nudged into a slow drift by an electric field that snaps into place far faster than their motion ever could. And once you see that, you can't unsee it. You start noticing how often the important part of a problem lives in what we ignore. geometry, boundaries, time, the difference between a transient moment and a settled pattern, the way empty space can be the stage where the real work happens. There's a practical lesson here, too. If a simple analogy helps you take the first step, fine. But don't move in and start living there. The goal is not to collect comforting metaphors. The goal is to build instincts that don't collapse the moment the situation gets even slightly subtle. So here's what I hope you carry with you when the screen goes quiet. The universe does not arrange itself to match the pictures we prefer. It arranges itself to match the laws. And if you're willing to trade a cute explanation for a true one, you get something better than certainty. You get understanding. Now I'm curious. What everyday thing do you want to re-explain now, once you're willing to treat the unseen structure as real? Thanks for watching. If you enjoyed this video, hit that like button, subscribe to our channel, and turn on notifications to stay updated on our uploads. And honestly, the next time you flip a switch, just pause for half a second and smile at how much is happening in the space you can't see.